yeah, there are so many good people at Trinity who can help. And if anyone has any questions for me after this, then do also feel free to drop me an email. I'm happy to answer any questions relative to subject or anything else. So today I thought I'd talk about the moon, try and tell you some things maybe you didn't know about the moon, from a science perspective, thinking about the past of the moon, so the history of the moon, what we're interested in studying about the moon now, and where moon science is going, it looks, in the next 50 to 100 years or so. And I also wanted to give a bit of an overview about what it's like to work in space science, but science in general. And maybe I can also offer some thoughts and advice about going through the system, university, placements, all that sort of thing, and even higher education up to PhD, because I've just been through the same situation. So the outline of the talk is basically this, so you can look away if you're very bored at any point. So I wanted to talk about my journey very briefly, and then I want to talk about what we think we know about the moon. So we probably all look at the moon from time to time, and for me, I didn't really know much about what was actually going on, why the moon looked like it did, for instance, until relatively recently. So I want to talk about what we think we know about the moon. I then want to talk about what we don't know about the moon and what are the big science questions at the moment that we as a world are interested in. And the biggest question mark at the moment, which I'll come to in detail later, is there water ice on the moon? What would it mean if there was? And how can we definitely say there is? And then what could we learn from that water ice? I want to talk about moon science that's happening not just worldwide at the moment, but also in the UK. And I'd like to talk about how you can get involved in space science. And I mean that in a broad sense. So although this talk is about the moon and my real specialism is lunar science, I also work on 2 Earth observation missions at the moment, one studying the polar ice caps, one is looking at crop yields in Europe, so that's a satellite orbiter. So I also work on a comet mission, and have some specialism in meteorites, etc. And yeah, have a pretty decent idea about what's going on in space science generally. And then, of course, we'll have plenty of time for questions at the end. So me, so I was definitely always interested in space science when I was a kid, but I can remember a particular moment staring up at space and being told that it takes time for light to move through the universe. And so if we see something that's very far away, we're actually seeing it how it was however many millions of light years ago. And that if someone sitting on a planet 65 million years away was looking at the Earth, they would see the dinosaurs, or the demise of the dinosaurs. And I thought that was pretty cool. And I just had always this fascination with space that stayed with me all the way through my university time, before I knew I would be in the space industry. And yeah, never ever thought I would end up in the position I am at the moment. And I was a PP kid, so I was on free school meals when I was young, and went to state schools, and didn't really know anyone in the field or anyone who was really a scientist. So I had a state school education in Southampton, and then did all my GCSEs, did A-levels in maths, further maths, physics, French and biology, so just an AS in biology, but had this interest in maths and physics always. And so did an undergrad in straight physics at the University of Surrey, which was awesome. And I was taught by Jamal Khalili, the chap from the BBC, amongst other people. When I was at Surrey, I still didn't know which direction I wanted to go. So the best thing to do, in my advice, would be, try things out. So I did a placement year in quantum physics first. That was looking at quantum computers. That was at the Diamond Light Source Particle Accelerator. Decided that wasn't for me. So there were lots of things about quantum physics that I didn't enjoy so much. And so thought, okay, what other subjects could I go towards? So I then went and worked in fiber optics for 2 different summer placements in Southampton. Had a great time, but again, wasn't exactly what I wanted to do. But I picked up all these transferable skills, you'll hear that word a lot, at university along the way. And so when I came to applying for jobs and PhDs, I had lots of skills that were useful for space physics. And so I ended up getting into a PhD in planetary physics at Trinity, at the University of Oxford. So my PhD was all about the moon, basically. So I'll come to what I was actually doing later. But essentially, I was an experimental scientist in moon science, which might not seem obvious. But we performed a study of the Apollo regolith samples. I'll come to what that means later. But basically, some moon dust samples that were brought back from the Apollo missions. And that was a lot of fun. And I finished my PhD, I handed in 2 months ago now. And so I've been a postdoctoral researcher, which is the step between PhD and professor at Oxford in the same group for the last couple of months. And hopefully we'll be here for the next couple of years. So first of all, I'd like to talk about what we know about the moon. So when you look at the moon, you will notice that there are these two distinct regions. So you've got the black or darker parts of the moon, if you will, the face or the rabbit in the moon, if you're Japanese, and what we call the highlands, which is the lighter area of the moon. And so you might have seen this and noticed this, but not known what is actually going on and why it looks like this. And you would be in good company, because we didn't have any idea really about what these two regions represented for a very long time. So even the Greeks, the Romans, they looked at the moon, asked the same questions, and didn't understand what the different regions what they were. So, for instance, some Greek philosophers actually wondered whether the moon had oceans, and that maybe these were the oceans in the dark regions and the light parts were land. So named those parts the Mare or the Maria, and meaning ocean. Some Greek philosophers thought maybe that the moon was a mirror and that it reflected what we saw, what would be seen from the Earth. And they tried to map out where the land and the oceans were to try and see if it matched up with the moon. And it wasn't really until the last 70 years or so that any decent discoveries have been made about what is going on the moon's surface and below. So what we do know now, and I'll come to how we know this later, what we think we know, is that there was a large collision between two enormous pieces of material, rocky material, and one of those was around the size of Mars, and one was the object which would now become the Earth. And these two things smashed into each other around 4.5 billion years ago. And the smaller one went into orbit around the bigger one. And at the time, they were magmatic, meaning that they were essentially covered in lava. So at that time, both of these objects would have been covered in lava. And because of that, none of the rocks from that period survive. So we can't study the Earth at that period. We can't study the moon at that period from, rock materials in the same way we'd study fossils. So the moon was much smaller, and so like a smaller cup of tea, because of the surface area to volume ratio, like a smaller cup of tea compared to a Sports Direct mug of tea, the moon lost its heat quicker. And because of that, the rocks on the moon started to solidify earlier than the rocks on the Earth. So the first thing that happened was that the least dense rocks created a crust around the surface of the moon, and underneath you still had all of that lava material. And so when we look at the moon today and we see the lighter regions, which we call the highlands, those regions are the ancient crust of the moon, which would have formed the original surface. We think then that what happened was there were some large impacts, so some enormous other pieces of rock in the early solar system that smashed into that surface of highlands material and created enormous holes in the surface. And so the lava from underneath the surface came to the top and created enormous lava oceans, which then solidified something like 4.2 billion years ago. And that is what you see when you look at the dark parts of the moon. So you have these two distinct regions on the moon, Mare and the highlands. So the other thing you might have noticed about the moon's surface is that it's covered in craters. So this is well known about them. So there have been impacts constantly on the moon's surface, and because there's no proper atmosphere, those impactors go straight and they smash the surface of the moon and they create craters and they fluff up the rock on the surface to create a very fluffy layer of moon dust. So from the moon's surface, we learn all sorts of things, but looking at that record of when those collisions were happening, when those craters were forming, we can learn about the number of craters hitting the Earth at the same time. And so we have a good idea that there was something called the late heavy bombardment, which was a period of very, very high number of craters being formed at the moon in the time of the lunar cataclysm, so about 3.8 billion years ago or so. And that's interesting because we think that the only reason for that could be, or one theory for the reason for that late heavy bombardment could be Jupiter and Saturn moved in the solar system from where they are orbiting at the moment, closer towards the sun and then further out again. And in the process, they brought lots of material with them and then out again, and it smashed into the moon. So these are some things we can learn about the moon's surface, but it's essentially been frozen there in time for almost 4 billion years, and it's been creating this record of the solar system from the craters. So we also know now, we think, things like the density of the moon. We understand something about what's happening internally in the moon. We know its temperatures down to the core and at the surface. And the question then is, and of course we know that it has this moon dust on the surface. So there's this fluffy layer of rocky material that's like rocky snow, which is called regolith from the Greek blanket rock. So the question is, how do we know all this? And most of it was learned in the Apollo missions. So in the 60s, America decided they wanted to go to the moon, so did Russia, and there were 6 Apollo missions that landed on the surface of the moon. The first one, obviously, famously Apollo 11, and there were 12 astronauts who landed and did various different scientific experiments. And previous to the Apollo missions, there really wasn't that much known about the moon. So, for instance, they didn't really know how deep that layer of fluffy material would be. So when they land, Neil Armstrong still doesn't know what's going to happen to his foot when he puts it on the surface until he does. And that's why there was that plate that he could stand on. So they wondered, some people hypothesized that he would just sink into the surface, like snow almost. Other people thought it would be much, much more solid. So the point being, we really didn't understand that much. So during the Apollo missions, they did lots of experiments. So they did seismometry, which is moonquake experiments, so looking at the rumbles under the surface, and that's how we know a lot about the inner structure of the moon. It was the first time really that humans had spent a considerable amount of time in space. So the Apollo 11 mission was only a couple of days on the surface, but the Apollo 16 and 17, they were driving around on buggies for a long period of time. And so it was the first time you really got to see, okay, biologically what's happening to a human body in space. And obviously it's something that's been thought a lot about with the International Space Station. But there are many jobs in biology now thinking about what are the differences for certain individuals if they spend a long time in space. How fit do you have to be to go to space? At the moment, there's a very small number of people who can, but in the future, could we lower the requirement? Why is it the case that women seem to have lower muscle degradation in space than men, and so make very, very good astronauts physically? Why is it that some people have more problems with their eyes in space, etc.? And this was also new, and no one had been able to study it before. They also took pictures of the surface. They gave eyewitness accounts. So I was once sat in a talk, and a researcher said, "Oh, you know, the whole surface of the moon is covered in moon dust." And in the front row was one of the Apollo 16 astronauts. And he put up his hand and he says, "No, it's not. It's not. I saw it." He says there were lots of rocks on the moon when I was there that weren't covered in moon dust. So these eyewitness accounts give you information that only a human can provide. They also studied the surface and the moon dust, but they also brought back a lot of samples. So there is 1/3 of a ton of moon dust and rock on the surface of the Earth, which was returned from the 6 Apollo missions. In Apollo 11, there was just 2 kilograms because they got there, they grabbed what they could, they put them in their pockets and they came back. But by the later missions, they were bringing an enormous amount of samples. And so the Apollo missions was really how we know most of what we know about the moon's surface and could actually verify what was going on there. So just before I carry on, I just wanted to give you another update about what this lunar regolith stuff actually is. So over billions of years, you have these collisions, and they grind up all that rock on the surface. And because there's no air, there's no water to smooth down those rocks and make them more like pebbles, what you end up with is fragments of rock, small pieces of rock, which are very spiky because they can never be smoothed. And these spiky materials, without any strong gravity pull, because the gravity on the moon is a sixth that of Earth, they create what we call fairy castle structures. That's literally what we call them in the scientific term. So they're very, very fluffy materials, incredibly high porosity. So they just sort of sprinkle down onto the surface, and there's lots of holes between them. So a crazy fact is that moon dust is so bad at conducting temperature because there's so little connection between all the different parts of rock. It's so fluffy that if you had 30 centimeters of fluffy moon dust, you basically have total temperature isolation from one side to the other. So if you built an igloo on the moon and you covered it in 30 centimeters of moon dust, you could heat it once and it would stay the same temperature, and you could have total absolute zero on the other end, which is crazy. Anyway, so this is what covers the surface of the moon, and this will become slightly more important later on. And yeah, here are some nice pictures of some of the rocks that were brought back from the Apollo missions. And this is, I've met multiple people who say to me, "Oh, can we prove we went to the moon?" And actually, when you look at these rocks under the microscope, you see that they've been altered by the radiation from the sun because there's no atmosphere on the moon, and none of the rocks on the Earth have that same property. So for 100% that these have come from space, basically. So what do we not know about the moon? Well, as I said earlier, we can't learn about planets from rocks, etc., before those rocks are solidified. So we don't really understand much about the moon or the Earth when things were very magmatic. And that actually leads to an important point. So one justification for studying the moon and other planets is that we can't learn much about the Earth pre 3 billion years, so before 3 billion years ago, from the rocks, etc. And we really don't know what the Earth was like to good confidence at that time, because everything was magmatic. You had the oceans, but the land was mainly magmatic, and so we couldn't see much about what was happening in the early Earth from the history of the Earth. But the moon solidified quicker. So by studying the moon at that time, we get a good idea about what was happening on the Earth. And this will become more important later when I start talking about the water ice that's potentially on the moon. We don't know why the moon is somehow different in the North and South poles. We don't really understand that much about the very, very center of the moon. So the core, has there ever been a magnetic field because of a core in the same way we have with the Earth? We have this iron core that creates a magnetic field. And the big question is there water ice on the moon trapped there? And can we use it as a resource? And I'll come to how that works later, and to why we think there might be water ice. So you might ask, how do we know things about the whole surface of the moon if we just went to a few different places in the Apollo missions, and also in the lunar missions from Russia and the Chang'e missions in China, etc. So there have been many orbital missions to the moon. So we can send a camera, for instance, or a thermal camera, and that will orbit the moon, and it can tell us about the large scale distribution of temperatures or what the moon looks like at different places. And so notable ones of these were, for instance, Clementine in 1994, Lunar Prospector in 1998. And that was very interesting because it was one of the first times we think we detected at the poles signals of what could be water ice. More recently, there was the Lunar Reconnaissance Orbiter mission. And one of the reasons I bring this up is the thermal infrared instrument, which is the part in the bottom right, which takes the temperature measurements. A large part of that was built in Oxford in our labs. And my supervisor built a large part of this mission. And so I'm part of the Diviner team. And the data from this mission is still being used today. So this mapped the temperature of the moon pretty much all around the surface and to down into the subsurface. It took pictures of the moon. If you go onto NASA and just look at what the Lunar Reconnaissance Orbiter pictures look like, they're incredible. It's the best data set of images we have for 98.2% of the surface. And it also launched jointly with this brilliant mission called LCROSS. So there was a question, could we, so okay, we can't study the water ice in some parts of the moon for reasons I'll come to in a minute. Could we smash a spacecraft into the surface and then look at the plume of dust that's kicked up from that crash and see if we can study it with telescopes on Earth? So that happened in 2011 with a mission called LCROSS that if you're interested in, we can talk about more later, but I think it's fun. So thinking about why we think there's water ice on the moon. So Diviner, the instrument I just showed you, took temperature maps for the whole of the surface of the moon, basically. And they realized that at the poles, in large craters, they think there are these regions which stay in permanent darkness. So the Earth has seasons because it orbits at 23.4 degrees or something relative to the sun. So as it goes around the sun, sometimes north of the pole is the north of the Earth is closer to the sun than others. But the moon orbits the sun at essentially a right angle. It's about 1.5 degrees or something. And so it doesn't have the same sorts of seasons. So if you imagine the moon orbiting the sun at a right angle, if you imagine then you have a crater at the pole, there are regions in that crater that never receive light or heat. And we think that they're permanently very cold. And if they're permanently very cold, the big question is, could ice be frozen there essentially forever since the beginning of the formation of the moon? And one of the big, well, I'll come back to the interest about it later. I'm trying not to jump the gun, and I'll leave it for the water stuff later. But you can see in these pictures these permanently dark regions in craters and poles. So this is, as I was explaining before, you've got the moon orbiting, and if you have some crater at the pole, the sun can come in, it can bounce off the sides of the crater, but it can't hit the bottom of the crater. And so the crater stays in some regions at minus 150 degrees Celsius, or even colder. So in Oxford, you might ask, what are we doing in terms of this and what I did in my PhD? So just as a quick side note, my PhD was essentially concerned with this exact problem. And this is the sort of thing you might do as a university project or later. So what I was doing in the last 3 or 4 years was essentially, we've been thinking about, okay, so if there is light hitting the side of a crater, and we want to know the temperature in a very, very dark region, so we know whether or not it could have water ice, we need to understand how that moon dust is reflecting light at different angles. We can put it into a thermal model. So for any physicists or mathematicians doing their studies at the moment, here's some nice equations. So these are the sorts of models we use to model how the heat works in different layers on the surface. And this was a setup I built in my PhD, which essentially does just that. It measures how a sample of moon dust, which is in the center there, you can see. So that's actually an Apollo 11 sample, which we were lent from NASA. How that sample of moon dust scatters light and transfers heat in lots of different directions. So you can see there a detector which moves across the surface, and it measures how the light is scattering. You've got a light source, which is simulating the sun, and then you've got your sample, and you can measure how that sample scatters light and transfers heat across all directions. So any engineers in the room, this is the sort of thing that you could be doing. We need the hands-on skills, and there's a lot of physics and maths that goes into this as well. But this was what I was doing in my PhD, is to make a database of how moon dust scatters light in different directions. And we did this for the Mare-like material, so that dark-like material from Apollo 11, and we did it from the light material from the Highlands from Apollo 16. Anyway, back on track. So what do I mean by ice volatiles on the moon, or ice on the moon? So these are elements which basically would evaporate into space if they were at, say, 100 Kelvin or above, which is minus 170 degrees. And on the moon, we think, as I said earlier, that these can exist in these permanently shadowed regions, which are those craters in the poles. And there's a nice picture of that in there in the top right. So those are regions which we've detected from that temperature mapper that we think, okay, these are cold enough. So the ones we're really interested in is water ice, for obvious reasons, and that should survive anywhere below 112 degrees. but we're also interested in things like ammonium and methane and all sorts. And so for the chemists and biologists in the room, one of the reasons we're really interested in this, and I guess the historians, is we don't yet understand how life formed on the Earth. So there are some big questions. You know, one of them I've seen in the chat: do aliens exist? Is there a God, etc.? How did life start? And we are pretty certain we won't find an answer from studying the Earth, because we think life began about 4 billion years ago. But we can't learn about the Earth from studying the Earth 4 billion years ago, because it was all magmatic. But we can learn about it from studying the Moon, the ancient Moon. And so if that water ice and those other organic materials like ammonium, like methane, nitrite, all these different things, if those organic materials, those carbons, nitrogens, oxygens, etc., have been trapped there ever since the formation of life on the Moon in those polar craters, could we study it and try and learn about what was happening biologically and chemically to actually work out how life first formed and in what way? And yeah, so there's a nice skating rink there, just to say that we think that this water ice is probably trapped and mixed within the surface. We don't think there's large ice skating rinks of water ice from what we see from the data. And we think that most of it will be trapped within the poles. So there's lots of reasons we care about finding and studying this stuff, not just, as I explained, thinking about, you know, how life formed, but we can also learn more about the solar system's history from this water ice, when it was delivered, etc. It's also incredibly useful because if humans wanted to go and stay on the Moon for a longer period of time, and that's a plan that at the moment NASA have, is to make what's called the Lunar Gateway, so some sort of moon base, which would then help us to travel to Mars, etc. Then having water there will allow humans to survive if we can properly use that stuff. But also you can use it for fuel. So yeah, and at the moment there's a lot of work being done. I know someone who's just finished a project which created this system which takes some rocks found commonly on the Moon, like ilmenite, which have oxygen and hydrogen in them, and you feed in the rock and out pops water. So water facilitates humans spending a longer time on the Moon, which would allow us then to go to Mars, etc. I've already explained that there's plenty of evidence that they're there, mainly from orbiting missions, but we can't definitely say that there is water there until a robot or a person has been to the Moon, dug it up, seen it, because it's such an enormous claim that big claims need big evidence. So what are we doing towards this search at Oxford and elsewhere? So here we are building these space missions ourselves. So at the moment we're working on, I've been working on it in the clean room this morning, we're working on a cube satellite called Lunar Trailblazer. We're contributing the Lunar Thermal Mapper to that mission. So this should basically make higher resolution, so much better pictures, similar to what Diviner was doing, both in the visible, but also in thermal infrared wavelengths. We do a lot of thermal modeling work, so we're actually trying to calculate what those temperatures are and where the water might be. And then we take laboratory measurements. So we measure things about the moon dust properties, for instance. And we've been very lucky that we have 30 grams of Apollo 11 lent to us from NASA and 90 grams of Apollo 16, which is apparently something like worth $1 million a gram. So we keep those very safe. And we also study various other airless bodies. And what I mean by that is comets and asteroids. So we've just finished a study of the Winchcombe meteorite, which is about to be published in Science, which was this meteorite that landed in the front garden of a family in Gloucester in last year, I think it was in February. And so, yeah, we're doing a lot of stuff, including all the Earth observation stuff. But we work in large groups, and we're working with NASA, we're working with the European Space Agency, and yeah, it's an enormously collaborative and worldwide and international thing, and there's lots of people in very good things. So if we can find this water ice, it should help us to constrain the scientific theories, but also allow us to think about traveling to the moon and then on to Mars. And this comes with a lot of geopolitical, legal, and economic things. So as well as thinking about biology, okay, how will humans survive in these conditions? How will it be safe? Who should we send, etc. As well as all the engineering and physics we'll need, we are starting to realize now that there are many, many unanswered legal questions which need to be thought about. So, oh yeah, and there's lots of future missions at the moment, not just these missions, the orbiters, but also we've been working on a robotic mission called Prospect with ESA, which was meant to launch on a Russian launcher, so it's a little bit up in the air at the moment, which was going to drill down and try and drill up some of that water ice. And also, before I go on to talk about the legal stuff, NASA are currently planning the Artemis mission, which many of you may have heard about, which is meant to send the first woman and the next man to the moon, probably in the next 10 years or so. I don't think 2024 is going to happen. But because of this, missions like Artemis, which is a nice schematic of here. So essentially the idea is to create a lunar base on the surface, which would then facilitate us being able to go to other planets, because it's much easier to get to Mars from the moon because there's much lower gravity there to launch off of. You can do it when the orbits are favorable, etc. And yeah, this is really something that we should all be excited about, I think, if we're interested in space science. But with that comes a lot of international relations, law, etc. So for instance, there are these things called the Artemis Accords, which are a legal basis for how countries and individuals should act in space. And these have been thought about just in the last couple of years. A good example of why we need to think about the law in space is you'll hear people talking sometimes about asteroid mining and stuff like that. And so the idea being, you know, could we go to this asteroid and bring back all of this platinum or gold that's on the surface or within the asteroid? And so they'll do a calculation that would say the mission itself to bring the asteroid here would cost $3 billion. But when the asteroid gets back, the materials are worth on Earth $5 billion. But if no one owns that material, then it's not worth that anymore, because all of a sudden you flood the market because there is so much more of this material on the Earth. So somehow someone has to own that material to be able to then sell it to other people so that it doesn't saturate the market. And this goes against what was always thought of about space previously, and this was in particular with the Apollo missions, etc. The idea that no one can own space, that you can't go to space and claim an asteroid as American or British or anything. And so there's a lot to be thought about in terms of how we go forward, and international relations. If we started a new community on another planet, should we throw away the idea of capitalism? Should it be some sort of other society? So there's social and political things to think about there. How should that society be set up, or should people still be related to their countries and the politics that's happening at home? Anyway, so there's lots and lots of various legal, political, and social issues, but I realise I've been going on for quite a while now, so I'm going to try and wrap up soon. So how can you get involved in space science? So I hope I've demonstrated that it all starts with your studies. So the good advice, I think, is to go with the thing you love and that you're most interested in and that you're good at, and become an expert in that thing. And then if you're interested, you can apply it to lots of different fields. So of course, if it's maths or physics or engineering or whatever, great, but space science needs biologists, it needs lawyers, it needs HR departments, it needs political scientists, it needs international relations, and all sorts. And so the best advice I had was from my dentist, which is just do what you love, and then you'll become better at that individual thing than other people, and then you can contribute to whatever field you're interested in. But the other thing which you can do, which is really useful, is to think about internships and placements. So I know that Dahlsbury has plenty of year-long and summer placements, and they do work experience and things for A-level students, the same as Rutherford Appleton Labs down south. So gaining some of those skills through doing placements for me was really, really valuable. And in the Oxford physics department, we have summer schools, we have work experience, we take A-level students, we take undergrad students at Oxford, and many of our PhD students start as master students or undergrad students who do work placements, and you'll often get paid for those. You can also start now, if you want, with citizen science. So there are large astronomy and otherwise projects like ClimateNet, like the Zooniverse, which allow people to do science and contribute to large projects, which still to this day computers can't perform in the same way humans can. So thousands of people go on places like Zooniverse and can classify what one picture is it a galaxy or is it something else, because humans are much better at this than others. So if you're interested, you can get involved in that way. And of course, doing a PhD in science is a great way to start with a project which is yours and something you're interested in, which you can do at the end of your bachelor's or your master's. You get paid for a PhD, and you'll get fundings, hopefully, so that someone will actually pay all the fees for you. So you can consider it like a job, but you also learn all these skills, get qualification at the end. And it's something you don't necessarily have to think about now, but it definitely helps if you want to move towards these sorts of fields. And so this picture, which is one I took in the lab of the Apollo 11 moon dust, this is the first scoop Neil Armstrong took, leads me on to ask, are there any questions? So I'm really open for discussions about whatever, and sorry if it was a bit of a ramble.
It wasn't a rumble at all. It wasn't a rumble at all. Amazing. Let's take some questions from Slido.
Yeah.
Again, around a theme, thinking about your motivations, your journey as well, which you've been kind enough to sort of bring us in on there. I'm looking to go into astrobiology when I'm older. Would you happen to know what's happening in that field currently, as I know it's quite a niche field?
Very good question. Firstly, I wouldn't, although I really do recommend the Oxford Short Introductions, I wouldn't recommend the Oxford Short Introduction to Astrobiology, which I read when I was an A-level student and didn't like at all. It was the only one I've ever read that I didn't like of that series, but it was very, very full of jargon. Sorry. So let me answer the question. Astrobiology, I suppose, from conferences I've been to recently, it seems like there are multiple streams of interest. So obviously there's the interest in how humans behave in space, which is one thing. Muscle degradation, how eyes are reacting, etc. In terms of what I was talking about earlier, how do those organic materials in the early Earth come together? This is an enormous field, and it's something people are really interested in. So the Harvard Smithsonian Center for the Origins of Life Lab is one in the States which actually tries to do experiments to try and answer the question of how organic materials, carbons, nitrogens, oxygens, etc., came together to create life on Earth. And they do all sorts of experiments. So I was at a talk about one which I thought was amazing. They were trying to come up with some physical basis for why DNA should be made of, A, T, C, and G in uracil. And they did this enormous experiment where they put all of these organic materials into this big soup in the lab, and they left it for 8 years or something with a pseudo sun light source, and they realized that that A, T, C, and G in uracil are photostable. So when light is impacted on them, they don't keep reacting with other organic materials, and they stay inert and stable for a longer period of time than the other sort of carbon-based forms which could create the backbone of life. And they've been trying to look at why is it DNA that works. And so this is from a chemical biology sense. So the biochemistry of life is something that's very interesting. A lot of people are thinking about how could life exist if it were different, the DNA forms, carbon-based life. So within exoplanet studies, and there's a lot of this happening in Oxford, actually, in our department. So Ray-Pierre Humber, for instance, is an exoplanets specialist. So in exoplanets, how could life exist there? Could it actually be made of methane or something else? And could life exist within the clouds of Venus, for instance? So there are these sorts of studies of exoplanets which ask, which exoplanets could harbor life, and then what might the life look like. So that's from another aspect. And then there are questions. So one big field for astrobiology is the study of extremophiles. So on Earth we have, so I do know some astrobiologists who actually mainly work on Earth, looking at these life forms in crazy places, hydrothermal vents or incredibly cold environments, or bacteria that live within ice in the ice caps and all these sorts of things. And the idea being, there is life on Earth that survives the most ridiculous situations and actually thrives in those situations. So by studying those life forms, could we get an idea about what life might be able to survive on, say, the moon in the ice caps or elsewhere? So tardigrades, for instance, are an example of a life form, these little water bears, and they just survive everything. They survive nuclear apocalypses, they survive being in space for a period of time, all that sort of stuff. And then the last thing I think I'll mention before I stop rambling on, because I could talk about this for hours, is, could life have come to the Earth from elsewhere? Could life have been transferred between planets, between planetary bodies, asteroids, etc., in the solar system? So there's something called panspermia, which is the theory that life on Earth may have been delivered here from, say, an asteroid or comet delivering organic materials to somewhere else. It smashes off of one planet, it lands on the Earth. There's another comet which hits Earth, it just distributes some life over to the same Mars, and Mars 1 billion years in, so 3.5 billion years now ago, was very, very similar to the Earth. It was at about room temperature. There was oxygen in the atmosphere, although there's mainly carbon dioxide. And there's no reason why, if we were, all of us were suddenly sent to Mars 3.5 billion years ago, if we had a bit of breathing apparatus, we would survive on the surface. So the idea being, could life have been on Mars and then distribute to Earth, or vice versa? So these ideas of how could the distribution of life in a solar system, panspermia, occur is another big thing. But astrobiology is a very new field, and it's always changing, and trying to keep up to date with, what papers are being published, or what books are being published about it is probably the best way to go about it. I hope that answered the question.
I'm just looking at themes. Let's get specific. Would a similar tectonic structure to Earth mean there's a possibility for earthquakes and volcanoes to occur naturally on the moon?
Good question. So earthquakes, moonquakes do occur on the moon, but the reason is different to the Earth. So the Earth is, as far as we know, I think, the only planet we know about which has plate tectonics, I think. Can't remember if there are any others, but I'm pretty sure that it's the only one we know about that has plate tectonics. It's unique in that sense. And so obviously we have earthquakes, not just from the energy within the surface and the fact we have this iron core, but we also have them from, as you know, right, the plate tectonics colliding together, etc. And that's the volcanoes, the rest of it. So the moon is, as far as we know, one solid structure on the outside. It doesn't have the same plate tectonics, but it does have internal heat and internal energy, not just from probably a similar core-like structure, which then you have this heat distribution, which leads to moonquakes, although they're less common. And the same on Mars, actually, you get Mars quakes. And a mission we worked on called InSight, which we built some seismometers for a few years ago, which landed in 2018. That's there to detect Mars quakes. Mars has a similar thing. You have this hot center, which leads to change in pressure and Mars or moon quakes. But the moon also has an internal heat source in that it has many, many radioactive rocks. And those radioactive rocks emit heat and keep the subsurface of the moon below that layer of fluffy material at something like 250 Kelvin. It's about, minus 50 degrees or something. It's not that cold because of these radioactive rocks emitting heat. So because of these two types of heat sources, you do get tremors on the moon and on Mars. They're just much less common than on the Earth because we have these plate tectonics. But I'd be interested to know whether there's any other planets that have been discovered with plate tectonics. But there's one thing that seems quite special about the Earth. But that answers the question.
Many suggest that life on Mars will be a possibility, something you sort of touched on in a very roundabout way. How realistic is this idea, and how far in the future might this be?
I have a bet on that in my career we will discover some form of very simple life in the solar system, either on Mars or on Europa, on one of the moons of Jupiter or Saturn. So for the reason being, we've landed on Mars a few times with robots. Each time it's been a very, very particular location, and until the recent landings, Perseverance and stuff, until those recent landings, they've always been the most boring place possible to make it easy to land. So the Jezero crater, which has been landed in recently, is very interesting, much more exciting and harder to land in. So we've only landed in a few regions of Mars. They've all been quite boring and haven't found any obvious detections of life. But we know, as we said earlier, we know that the temperature, the fact there was water flowing around Mars's surface 3.5 billion years ago, etc., led to conditions in which many life forms which exist on Earth would have existed on Mars. So to me, there seems no reason why life couldn't have already formed on Mars then. Then over this period of so many years, Mars, again, like we spoke about the cups of tea earlier, getting colder quicker because it's smaller, loses heat, and cools down quicker than the Earth. So Mars gets cold, meaning that most of its surface might not be habitable anymore. But that doesn't mean that that's true for the subsurface. And as I said earlier about astrobiology, we see extremophiles which exist on the Earth in places very similar to what we see on Mars now. So I'd say there is definitely a non-zero chance there is life somewhere on Mars under the surface or in favorable conditions or in old craters or something on bedrock of flowing water. It's just that we have to find it, and it's an enormous place and hard to study under the surface. Europa, Enceladus, all these other places, Titan. Europa is, to me, it seems definitely possible that life could exist there because you have this huge cap of ice, and then underneath you have an ocean 4 times as deep as the ocean on the Earth, just full of water. Everywhere on Earth, we find there could be life. There is life, So some people believe there is really something special about the Earth, and that discovery would be equally as amazing if that were to be the case. But if we apply the same logic to the Earth as we can elsewhere, which is the case of physics, this is exactly what we can do, then saying there is grass in one garden, and we know there's grass in another garden, and we know there is grass in gardens in Japan, why not, the same thing applied upwards? So I think there's a very high chance that we'll find some very simple form of life in the solar system, probably in our lifetimes. Personally, that's how I feel. Will it be conscious thinking life like us? Probably not. And that sort of life is almost certainly incredibly rare because even in the Earth, if you think about the history of the Earth, it's only the last sort of 2 weeks, if the Earth was a 50-year-old person, that humans have existed. Before that, dinosaurs for a long time, and then just sort of fire and madness. And so intelligent life, much less common. Bacterial, single-celled or otherwise life, I think probably much more common.
Although, of course, one thing may lead to another. And also, you've put your money where your mouth is, literally, on that one, haven't you, by the sounds of it, with a bet. Another big one, in terms of scope, is there a possibility we can prevent the effects of climate change by using resources from other planets?
Really good question. There's 2 answers to this. The first is the study of climate change is advanced by space science. So the only way we can prove and then do anything about, climate change is through studies of the Earth. And this is something we're doing a lot of at the moment, looking at the farms in central Ukraine, for instance, how the crop yields are changing because of temperature changes. And then if you can learn about what's actually going on from space, okay, can we do something to counteract it? Same with the ice caps. So we work on a mission called Pre-Fire, which is measuring how the ice caps are transferring heat and then making models. And you can take these to most politicians and try and convince them to make change from the ground up. Advances in space that might help Earth. Well, some people might say that, if the Earth were to be doomed, we could start a colony elsewhere. But it's likely that wherever we went would still be less habitable than the Earth at that time. The technology that is developed for space is always useful in ways that we don't first realize. You know, so the space blankets, those MLI blankets, the multi-layer space, you know, silver blankets that are now used in medicine, and ambulances have them, and marathon runners have them because they're so insulating. This was developed for space. And there are many examples of things which have been developed for the space industry which then help the climate. Although there are other examples of things in the space industry which really damage the climate. So rocket fuel, and there's an enormous question at the moment about how to balance that, because the space industry is so important for you know, the climate catastrophe and studying it and doing something about it. But it's also damaging, and aerospace, you know, planes is also damaging. So technologically, there are lots of advances. If we could make much more efficient, you know, flight, or if we could come up with some way of doing it sustainably, or etc., then technologically there are advances which can help us on Earth. But that's a very good question, and it's something I probably don't know much about, and I'm not sure any of us know. You know, this climate problem is enormous, and it feels like it needs to come from both directions, both from the bottom up, if you will, from societal and individual changes on a large scale, as well as from the top down technologically and everything else. So yeah, I feel like I'm not placed enough to answer, actually.
It's refreshing to hear somebody say that, isn't it? Do you think, a very specific this one, and the last one that we've got time for, do you think a medicine degree is transferable into space science? And I guess to extend that, do you think other degrees are extendable into coming then into a space science sort of specialism?
Absolutely. Absolutely. So very directly, many of the people who work in mission operations in NASA are medics who are constantly thinking about the state of their astronauts in the ISS or whatever, and thinking about, you know, are they healthy? What's going on with them? What do their vital signs say? So there are medicines, doctors who are actively working on all crewed space missions, and in the future that will be really important. But also just learning those hard skills, being able to do something with your hands, being able to work under pressure. There are multiple astronauts currently working who started from a medicine background. I think, you know, as I'm a demonstration of, finding one thing that you're really interested in, gaining those skills, those hard skills, and showing that you can do your thing, you know, and then you can definitely apply that in different directions. And medics have an enormous list of skills, working under pressure, working with their hands, talking to people, etc., which would be very valuable. What else? Yeah, that would be my answer for medicine. But with, you know, if you were to go on the career sites from the European Space Agency or NASA or something, and just see what they're looking for, and you'll realize there's an enormous range of things. And medics are always useful because, you know, they can save lives and stuff.
Ron, thank you so much for sharing all your ideas today, not just on the lunar science, but also on your own sort of journey here, and for taking so many questions on such a diverse sort of range of fields. Greatly appreciated, and I know we'll have quite a few people watching this on a recording too. Thank you to those of you who joined us this evening. Really appreciate your being here and you're asking all these questions. Over to you, Ron.
Thanks so much. Thank you for having me. It's been great.
Cheerio. Goodbye.